Hi there and welcome back to Chapter 1.3 from Stevens' Matrices, Vectors, and 3D Math. This is the second video from this section. Before I go to where I left off, I'll do a brief review of what we covered in that first video. So we were talking about inverses and determinants. All right? And an inverse for a matrix is another matrix such that A times its inverse is equal to the identity matrix. That's just like 3 times 1/3 equals 1. This here is the inverse of 3. And likewise, 3 is the inverse of 1/3. What makes them inverses is when you multiply them together, you get 1, which is the multiplicative identity. So we're doing the same thing in terms of matrices. And we had a formula here for the inverse of a 2 by 2 matrix. And part of that formula contains a number out in front which has AD minus BC in the denominator. That number is called the determinant of that matrix, meaning if that number is 0, right, if we get a 0 in the denominator, you can't do that. So if we have a 0 for the determinant, there is no inverse. All right. We showed that having this inverse is nice because if I have a system of equations, this system of equations, a system of equations, if I write it in form of a matrix equation here, I can then just symbolically solve it in terms of the inverse of A. All right. Let's see, what else do? We did an example. We did some inverse theorems. And then we showed how to get the inverse of a larger matrix. Right? You have a formula for a 2 by 2, but to get a larger matrix, what we do is we create this super augmented matrix where you have the original matrix A on the left, the identity matrix on the right. And you go through a sequence of row operations. And if you can get the identity matrix on the left, then this matrix on the right is the inverse of your original matrix, if you can do it, right? So you have to be able to row reduce this thing to the identity matrix. All right, so as I just mentioned a couple minutes ago, the determinant of a 2 by 2 matrix determines whether or not the matrix has an inverse. And we use, so we're going to be taking determinants of all matrices. And the notation will be det A, that's for determinant of A, or we can also use the absolute value representation. So when you see the absolute value of A, you got to try to remember that doesn't mean the absolute value that you're used to taking with respect to real numbers. It actually is talking about the determinant of a matrix. And as mentioned earlier also, the determinant of a 2 by 2 is AD minus BC. And if the determinant is 0, the matrix does not have an inverse. Right? So, and that's the property we want to get to. We want to calculate a determinant. We want to tell ahead of time whether our matrix has an inverse. Right? And we can do that by finding its determinant. Now with larger matrices, there is no closed formula. It's more of a process. Right? It's called a cofactor expansion. There's some definitions, there's some terms in here that it's not entirely important that you know these terms. I'll just go through the process, and the process is defined in these terms. But you'll see the procedure, and hopefully after our third little example down there, you'll have it. But suppose I start off with a square matrix A. The minor, the ijth minor of A, looks just like A, only you remove the ith row and the jth column. And then the ijth cofactor of A is just the determinant of that minor times -1 raised to I plus j. And we'll first show this in terms of expanding across the first row. So what that means, this A1, that means I'm going to take this first term in my matrix A, and then I'm going to multiply it by the cofactor, which is just the determinant of this matrix that's remaining times -1 to the 1 plus 1. And then you continue across A1, 2, this times the minor associated with it. So it's the determinant of the remaining matrix times -1 to the 1 plus 2, and so on. And you can also expand along. You don't have to expand across the first row. You can expand across the second row, third row. You can even expand across any column or down any column you want. Okay, so let's show some examples, because this just using the terminology probably leaves you a little bit confused. So I'm going to start off with my matrix A. So I will expand across the first row. So the first thing I have is that 2, right, times the determinant of this matrix. Right, that is right there. Times -1, that 2 is in the 1, 1 position, so it's 1 plus 1. Then I move across to my 4. And I multiply by the determinant of this matrix that's remaining, times -1, and now I'm in the first row, second column, so I raise -1 to the third. And I complete my expansion by taking my 6 here, times the determinant of this matrix. All right, that's 1, 0, 1, 2, 3, that's right there. And then I need to multiply by -1 to the position of my 6 there, which is the first row, third column. So once I have this all set up, now it's just a matter of multiplying and adding and getting determinants of 2 by 2s. Okay, so I come here, I have my 2 times -1 squared, so that's just 2. The determinant of this matrix is -1 minus 0. And then this is 4 times -1 cubed, so that's -4, times the determinant of this matrix, which is 0 minus 0. And then I have 6 times -1 to the 4, so that's just 6, times this determinant, which is 0 minus 2, right there. So you distribute, add, subtract, you get -14. So the determinant of this matrix, det A, equals -14. So the nice thing I know is that A has an inverse, because the determinant is not 0. Right? There's 2 types of determinants, 0 and not 0. If it's not 0, you have an inverse. If it is 0, you do not have an inverse. Okay, so I can also expand across the second row, and that actually turns out to be very friendly. All right? So let's expand across the second row. So that means we're starting here with this 0, is right here, times the determinant of this matrix, but it doesn't much matter because I'm multiplying by 0, right? And then you'd multiply by -1 to the position of that 0, which is 2, 1. 2 plus 1, right? And then I would continue across 1 times the determinant of this matrix, 2, 4, 2, -1. There's my 1, 2, 6, 2, -1, and I have to multiply by -1 to the sum of the indexes of this of the 1 here. So that's second row, second column. Then I continue across. I have a 0 here, right there, times the determinant of this matrix, 2, 4, 2, 3. And then I have to multiply by -1 to the second row plus third column. All right? And the nice thing is, these zeros mean that I don't really have to much worry about what that is. All right, 0, those determinants, the -1 to the plus or minus, it doesn't much matter. I'm multiplying by 0. So all that's left is this middle term here. I have 1 times negative 1 to the 4th, that's 1 times 1, which is 1, times the determinant of this matrix, which is negative 2 minus 12, which when you add those up, you get negative 14. Same determinant as when we expanded across the first row. And finally, you can expand across any column. We'll expand across the first column. So I'm going to be working down. So I have 2 times the determinant of this matrix times negative 1 to the 1 plus 1. That's the first row, first column. Then I go down to my 0 times the determinant of this matrix, 4, 6, 3, negative 1, times negative 1 to the second row, first column, 2 plus 1 plus 2, or 2 plus 1, doesn't matter. And then I continue down, there's my 2 right there, times the determinant of this matrix, times negative 1 to the third row, first 3 plus 1, or 1 plus 3. Right? And then I just have to get my determinants, do my multiplication, raise negative 1 to various powers. And what do I have here? This first part is 2 times negative 1 squared, so that's just 2, times negative 1 minus 0, right there. Then I have 0 times negative 1 to the third, so that's negative 0, I guess. Doesn't make any difference. There's a 0 times this determinant, negative 4 minus 18. Again, doesn't much matter. I have a 0 out in front. Then I have a 2 times negative 1 to the 4th, so that's just positive 2, times this determinant, which is 0 minus 6, negative 6. And when you distribute, cancel, and combine, you get the determinant is negative 14. Just as we had, expanding across the first row and the second row. So you can expand across any row, any column. Alright, so a little warning here, that cofactor expansion, not only is it difficult to do by hand, but even programming it with a machine and having a computer do it, it becomes calculation intensive to the extent that it will be difficult for a machine to even do it if the matrix gets too big. There's another way around it, and the way that it's really done is you do Gaussian elimination until you have a diagonal matrix. And you can take the determinant of that diagonal matrix and transform it back to the determinant of the original matrix. But we'll be letting software do that. But it does sort of bring us up to this first determinant theorem. If A is a triangular matrix, it can be upper or lower. Suppose it's 2, 3, negative 1, 7, 5, 6, 0, 0, 0. Or, so that's upper triangular, or lower triangular, where we might have 1, 3, 4, 7, 9, 2, 0, 0, 0. So this is upper, lower, and the determinant of such a matrix is just the product of the diagonal elements. So the determinant of this matrix is negative 6. The determinant of this matrix is 1 times 3 times 4 is 12. Right? The determinant of A transpose is equal to the determinant of A. That should make sense because you can expand down any row or column, and all the transpose does is transpose rows and columns. The determinant of AB is equal to the determinant of A times the determinant of B. That's nice to have. The determinant of the inverse of the matrix is the inverse of the determinant. That's nice. It is required beforehand that A is invertible so that I actually have a determinant that is not 0. Now we're going to do our first version of the super theorem. And what I mean here, what this is saying is that the following are equivalent, meaning if you have one of these, you have all of them. I'm going to work from the bottom up. Suppose you know that the determinant of the matrix is not 0. That is the same as saying the matrix is invertible. That is the same as saying AX equals B has a unique solution no matter what B is. That is the same as saying you can get the identity matrix from A through a sequence of row operations. Right? So all of these, if you get one, you have them all. And that's great, because that means if I can find the determinant and it's not 0, I've got a unique solution for any equation of that form. It means that it's invertible and it's row equivalent to the identity matrix, which is less important. Okay, in this next little piece, I don't have MATLAB on this particular computer, so I'll just go over what we're demonstrating here. And really what we're demonstrating is the determinant function in MATLAB. It's just det A. So if you put in A, take det parentheses A, it will give you the determinant. And if you take the determinant of the example we did, it will return negative 14, as we figured out 3 times in a row. And then you can get the inverse of A with just inv, INV A. And if it has an inverse, it will spit it out. If you take this matrix B, get its determinant, it has a determinant of 0. All right? And remember, if the determinant is 0, there is no inverse, but that doesn't prevent you from trying to find it. If you do inverse B, you will get a warning. All right? And then the inverse theorems. One of the exercises has you demonstrate all of the inverse theorems, but this is just one example. All right, that's the theorem that the inverse of A inverse is just A. So all you do is take the inverse of A, and it should return A. And then some of the determinant theorems, and again, there's a assignment where you're supposed to demonstrate these with MATLAB. They're not proofs, they're just demonstrations. For example, if you create an upper triangular matrix D, then the determinant should be 2 times 3 times 4, and when you do that, you indeed get a determinant of 24. So it's just playing around with MATLAB using the det function and the inverse function. All right, and so I want to get a little bit into solving matrix equations, because once we can take a system and put them into matrix equations, we can then solve for the unknowns. But in the future, we're going to be doing transformations with matrices, and we'll want to know where the transformation takes us or where we originated from after a sequence of transformations. So we are going to be going back to an old favorite where I say solve for x. Right? Only now you're not in high school algebra, we're doing matrix algebra. So for example, if you have this equation, I say solve for x, it's right there. The first thing I do is subtract y from both sides. And when that happens, the y disappears from the left. I have that. Now I need to multiply ax by A inverse on the left. That is very important, because then A inverse is right next to A. That turns into the identity matrix, which is the matrix version of 1, and it disappears, right? And it's gone. Right? And so you have to remember, multiply on the left by A inverse. Right? Because usually what you'll do is you'll just have AX equals B minus Y, and then you'll have X equals A inverse B minus Y. That's generally, you wouldn't show the multiplication. But you do have to remember it's on the left, because if you had started with this equation and said, all right, x equals b minus y times A inverse, you might not even be able to do that. Remember, it matters left or right multiplication. So if you multiply on the left over here, you have to multiply on the left over here. Right? And so when you go through that process, you can get x all by itself, A inverse times the quantity b minus y. Suppose I have this equation. I'm going to solve for x. Now I could distribute my A, but instead I'm going to just multiply on the left by A inverse. Right? That gives me this equation, subtract y from both sides, and I have x all by itself. Okay, this equation, I'm looking to get x. So I'm going to multiply on the left by A inverse. So notice it disappears from the left-hand side and it appears on the left of B. Then I subtract y from both sides. But now I have this B, and I need to get rid of that, so I multiply on the left by B inverse. Right? By the way, I've been writing a lot of A inverses and B inverses, and there's a reason for that. It's because we are assuming that A and B are invertible matrices. If we didn't know that, just writing A inverse, there might not be an inverse, but we know that these inverses do exist. So for our last example, I'm going to solve for x, but there's a couple of them in here. So the first thing I'm going to do is distribute matrix multiplication across addition, which is one of the properties, the distributive property of matrix multiplication. So that means I have my x separated out. I have ax there, bx there. I'll subtract bx from both sides, subtract ay from both sides. And I get to my third equation there. And now I can undistribute, also known as factoring. And notice it's important that you're going to factor on the left, right? That's a minus b times x. It is not x times a minus b. Right? Because that would just give you xa minus xb. There's a good chance you can't even do that. So we factor. We get a minus b times x equals the stuff on the right-hand side. And so what I would like to do is just multiply on the left by a minus b inverse, and I would get x by itself. I will have solved for x. The problem is a minus b might not have an inverse. Right? Just because a has an inverse and b has an inverse does not mean that a minus b has an inverse. And a simple demonstration will show you that that is the case. So here's a matrix with an inverse. Right? Its determinant is 1. Right? And I'm going to subtract another matrix that has an inverse. Right? This has an inverse. This has an inverse, but when I subtract them, I get 0, 0, 0, 0. That determinant is 0. There's no inverse. So there's no guarantee that a minus b has an inverse. Sometimes it will, sometimes it won't. So the next video will just be the summary worksheet, where we're going to use MATLAB to get the coefficient matrices from these systems, and then find the determinants and the inverses, and see how that relates to whether or not there's a unique solution, and whether the system has infinitely many solutions or no solutions. But that'll be the next video. We'll do that. We're about done here. This is already getting pretty long. Okay, so I'll see you at the worksheet. Bye.